So last week, we saw how to prove the correctness of some transformations on our small programming language. And towards the end, and that was a teaser for this week, we saw that we could define the identity transformation, which of course preserves correctness. And then we could compose transformations. And if both of them are correct, then the composite is also correct. And what we're going to see today is actually some kind of abstract setting in which we can talk about things that can be composed. So the idea is to, instead of doing a lot of busy work every time we work in a structure that has this compositionality in it, we do the work once, and then by instantiating it to different settings, we get all of the proofs for that one setting in particular. So who was saying that the other day? Oh, yeah, I was watching some like VFX guy saying that whenever he writes the same thing, he does the same operation 3 times, basically, then he writes a script for doing it. And in programming, it's the same, but one level up, right? Whenever you have the same pattern, like showing up 3 times and you're bored of copy-pasting, you just introduce an abstraction that does the job for you. All right, so, but first we're going to start in a slightly simpler setting because when we talk about functions and compositions and so on, we have types that are flowing in and out of the functions. But basically the bare bones version is monoid. So you should have seen monoid in first year, I believe. At least in third year, in the Haskell course, we are talking about monoids. Except that in the Haskell course, of course, we don't enforce the laws because there's no language to express proofs in Haskell. So we're just saying the best we could do, and we sometimes did it actually, is to have properties for automated testing so that whenever you throw in a new instance for a monoid, then at least you have some kind of like sanity checking that the properties you claim to hold are holding true. But of course, the properties are not demonstrating the absence of bugs. They can only uncover existing bugs. But because they're not proofs, and they're not necessarily covering the whole, they're not covering the whole space, you can always have corner cases you haven't explored and that are actually not implemented properly.
Yeah, you need, sometimes testing is enough to prove theorems, but you need to know something special about how simple things are. Sometimes, like, you know, if you've got 2 quadratic formulae, if they agree at 3 points, they agree everywhere. Sometimes there are results which say, look, it's only this complicated, so this much testing is enough, but they're quite hard to find.
Yeah. All right, so we're going to define monoid, and then we're going to insist on getting proofs that the implementations we're giving are actually abiding by the monoid laws. So as always, when you want to pack a bunch of things together, you declare a record. And what we typically do, but there's wiggle room here, is to put the carrier as an index, because then you can say, I have a monoid over the natural numbers, I have a monoid over integers, and so on. Sometimes you might also index it by the operations, because it's not enough. Sometimes you want to insist that the monoid on the natural numbers you have is max, but it could also be plus if you're just saying it's a monoid over the natural numbers. But in this instance, we'll just index by the carrier. And we'll say, well, we have an operation called this thing, just like in Haskell, that takes 2 values and returns a value of type X. So that was for the, if you remember, the semigroup parts of the monoid definition. And what we said in the semigroup is that, so semigroup first, is that this operation should be associative. So what does it mean? It means that for x, y, z, it doesn't matter how I parenthesize the x, y, z operation. I should get the same results every time. Okay, so here some alarm bells should be ringing, right? Because we're talking about propositional equality. But last week we saw that in our example, propositional equality was not good enough unless we assumed functional extensionality. So here, for the sake of simplicity, I'm not going to depart from propositional equality, but in reality, you could have here not only an x, but an equivalence relation over x, which is our internal notion of equality we would use for the definition of the monoid. And then here you would insist that the computations are only equal up to that relational equivalence. Of course, it makes things slightly more complicated because then you don't have all of the beautiful results you have over propositional equality. You don't have access to rewrites. You don't have access to congruence necessarily automatically because you need to prove that your functions are respecting congruence and so on. So for this exposition, I'm going to stick to propositional equality and just assume functional extensionality if I need it. But in practice, you probably don't want to do that. You probably want to be a bit more subtle about your notion of equality. So that's the rules for semigroup. And if you remember in Haskell, you define a monoid by saying, well, I have a semigroup already, and now I'm going to add a neutral element, which will have no impact whatsoever on the crushing or crunching, whatever you want to call it, operation. So, I mean, I'll stick to Haskell style. I'll call it memty. You don't like that?
Not a fan.
Okay. What do you want to call it? NEU, okay. And what we want to say is that if you put new on the left, it's as if you had done nothing. And then if you put new on the right, it's as if you had done nothing. Okay? So here I am adopting conventions that are quite common in the standard library, where you basically describe the shape of the interesting side of the equation. It's good to have naming principles because as your libraries grows, you're struggling to find even the results you're looking for. But if you have a good naming strategy, then at least you can sort of guess where they might be and look for them. Examples of your favorite monoids. Well, do you have an example? I've added something, some imports that are suggestive.
I think there's a reason why we should start with lists.
All right, so let's do lists. So for any set, for any set, we can prove that list of x is a monoid, which is quite nice. Oof. Okay. Let's try. Okay. Let's open monoid and then split. So it looks a bit better. Still not great, but so to define a record, as always, you can either build the record using the record keyword and then list all the fields, or split on the left and then explain what it is you're doing on the right. Although here it's not going to make a huge difference because I've imported all of my definition. Well, not all of them, but soon I will have. Okay. So how do we combine two lists together? Well, we could pick the first one, pick the second one, append them the other way around. We could interleave them or something, but we need to remember that it needs to be associative. So interleaving probably is not associative. Throwing one away is right. If you're throwing the left one away, and then oh no, if you yeah, no, it works. But then to have a monoid, it needs to actually respect the neutral laws. And the neutral laws, what they're saying is that this operation doesn't really throw any information out, right? Because if you put in like the neutral value, and it needs to be the same neutral value no matter what x you're passing in, then you should be able to recover x from it. So if you're throwing the left one away, the second equation will not be verified because you will have discarded x, and now the neutral needs to be equal to all of the x's. And if you have non-trivial x, that's just not possible. If you throw the right one away, it's also not satisfying the other equation. The interleaving we said was not associative. What else did I say? You could append them the other way around, like the flipped version. Would that work? Yeah, I think that would work actually. But in our but it feels a bit unnatural to just decide to flip things around. So I'm gonna stick to plus. So I was a bit ambitious here, bold and in that when I define my notion of monoids, I say that all of the arguments were going to be implicit, meaning that whenever I use it, I will be able to reconstruct like all of these values. But of course, I mean, by these laws alone, we already know that you could have a nu anywhere you wanted. So when you're parsing the thing, you could say, well, it could be x, y, z, or it could be x, y in this bit, and nu here, z, and these should still be equal to each other, meaning that the like goal-directed reconstruction, unification is probably not going to be able to figure out these solutions because they're not unique.
It's even more ironic than that, because the only situations in which x, y, and z will be invariable is if this thing is a constructor. And if this thing is a constructor, then this equation will be false.
Yeah. All right, so let's make them explicit then. For these ones, I think, okay. For the neutral laws, I think I can still get away with it because you have an isolated x on one of the sides, meaning that it's always possible to unify a variable with an arbitrary expression, as long as the variable is not mentioned in it, but here there's no risk of that. And so that will always be it will always be possible to figure out what the x should be just by looking at the right-hand side of the equality we're trying to apply the lemma to, or the theorem to. Okay. So going back to this one, well, now the type should actually line up precisely. Oh. If I can type it. Yeah, there we go. Because the standard library is well designed and they're aware that it cannot be inferred. And then I need to find a neutral element for appends. I mean, there's no price for guessing. First of all, you have an arbitrary x, so you have no way to build a value of type x. The only thing you can do is use the empty list. And then it is indeed the case that if you, it's plus plus identity, right? So this is just, aha. Oh yeah, I always get confused because like this symbol is on the right, but the nu is actually on the left. Okay. And in this instance, well, even if we ask Agda not to compute, it's already fired enough. Like the empty list append X is gone. And so this is just trivial by computation. Nice. Now I'll do my favorite one. I don't know. Yeah, I mean, you see where this is going. Okay. I could have named this maybe, but whatever. Should I name it actually? It might be good to name it. All right. Right, so my favorite type of monoid is the monoid of all the functions from X into itself. And this is basically what we saw last week at the end, right? When you have an identity, when you have composition, you can combine them arbitrarily. It doesn't matter where you're putting the parents, they will all be equivalent.
So do you really need to do this wrapper type? I mean, I guess you're just trying to say, I would just think, because you're not doing the type class thing.
Yeah.
So, you know, where you can only have one. So, like, numbers are monoidal in lots of ways.
Mm.
None of them. And a whole load of new types, but wrapping up numbers so that they can be seen as all of these different models, is then set magically to infer the structure from the type, which is silly. Have structured in multiple ways.
Mm.
So we're not doing that. We're saying, here's a record, we're going to pass around explicitly. So we don't need to make wrapper types for things that just to make something get with structure. Not for that.
Okay, so the first thing we need to do is figure out a way to combine two functions into a single function. Well, that's composition is a good candidate for that. And then we need to prove that it is associative. So I'll get my hands on X, Y, Z. That's the one from the standard library. So it's the Haskell style composition. Whenever you have a tech like this, it's to mean the non-dependent version, because with respect to inference, it has a better behavior. But you can see that it's defined in terms of this other one, which is the horrible type. Yes. Okay. And then we need to prove that it is associative, and that's the beauty of it. We do a bit of normalization. We have some mixture of eta expansion, right? If you remember, or maybe not even, because I think it may be defined as a lambda, but whatever. Any function is equal to lambda x applied to that function, f, lambda x f of x. And once you've applied the composition to one argument, no matter how it is defined, it will start reducing. And it is defined as nesting the calls. And so when you nest the calls, well, they're nested exactly the same way. And so these things are just equal on the nose. It's one of the rare cases where even though you're using functions, you don't need functional extensionality. There's just enough computation for everything to go right. And then we need a neutral element. Well, the neutral element is the identity function, because when you compose with the identity, it doesn't change anything. And here it's the same, right? You have, well, okay. You had just enough computation on the left-hand side to reduce to this. And then this is actually equivalent. So x is a terrible name for it. Here it should be f, right? You have f equals lambda x f of x. And of course, that is true, even though the goal is not displayed as something being reflexive. Because of the eta rules, when you claim it is true by reflexivity, AIDA will check it and will be like, oh yeah, my bad. I should have printed the nicer goal, maybe.
Okay, but yeah. Invent a new name. See what happens. Try applying both sides to the same hypothetical expression.
Mm. And then for the next goal, neutral on the right, we get exactly the same goal. And that's because identity computes away, right? So no matter whether you put it on the outside of the call to x or inside on the argument to x, it goes away anyways. So you end up with exactly the same thing. And that's how you prove that functions from x into itself form a monoids. It's the monoid of just pipelining, basically, right? Okay. Do you want to do generic programs over monoids? So the idea, well, yep.
What are you trying to get me to do?
So first define folder and then a bit of shuffling around.
Okay.
And then eventually you notice that.
Right. Let's play this game. Okay, so if you're a Haskellr, then you have this operation that kind of bottles your basic recursive computing pattern for list functions. Namely, what do you do with the empty list? What do you do with x cons x's? So there's you got some type t, you got x and t in set, and you've got some way to do an x to a t to get another t, and you've got some basic t to start from, and that means if you've got a bunch of x's, you've got a way of making a t. This, I hope, rings a bell. And I've got my tomato sauce of undefinedness, and I'm going to call these suggestively cons and nil. Oh. Right. And what do? We, of course, we look at our list. Oh. And we turn the list nil into our t nil. And what do we do with cons? Well, we have a way of consing an x onto a t. So we do cons with our x, and then we get our t by computing recursively. So we turn the list conses into our cons function, we turn the list nil into our nil value, and we build up a t the same way we were building up our list. Okay so far? Right. I think I should probably let me just label this, no, version 0. I'm going to do multiple versions. Reload. Oof. Now. Oh, what? So my first refactoring that I'm going to do to this, simply to adjust the order of the inputs. The thing that gets me is that I've got T arrow T here, and I'd quite like T arrow T here, just because it looks nice. Oh no, I've toggled overwrite mode. Let me figure out how to untoggle that. Good. Classic. Right, I could fool about with rectangles in Emacs, but I'm not going to. Right, so all I've done is moved nil past the list on the left-hand side, on the right-hand side. Everything's still cool. Okay. Yep. Well, I will need a third one anyway. Right, okay, now my next trick, I noticed there's not very much exciting happening with these. You know, I've got a nil here and I output it straight away. I've got a nil here and I just thread it through. So I'm going to do a little bit of code golf to get rid of it. Step one, I move that away and I turn that into the identity function. Step two, I get rid of that. I'm going to get rid of these parentheses. And now I need to know how to type that. Oh, no. Like that. Oh, okay. Are we lucky? We are lucky. So, what do we notice? Right. We have just turned the neutral element of my favorite monoid into the neutral element of Guillaume's favorite monoid. And, well, if you imagine this is true for individual consas, and you make lists by doing a whole bunch of consas, it's going to turn out that we're also turning the operator of my favorite monoid into the operator of Guillaume's. So what I'm going to do is I'm going to define a thing called fold map, which takes an x and a t in a set and a monoid over t, and it gives us a function from list x to t. Fold map is, what do I want to do? I'm going to say fold map m, little m, is go, where open. Oh, you've opened Monoid already, right?
But is it going to be incompatible?
I'm not going to risk it. Oh. Oh. Right. So I look at X's.
Well, you could at least name the module, even if you don't open it. This way you can fully qualify for versions.
Well, I'll let you refactor that in a minute.
Okay.
Right. Oh, sorry, my bad. I need one more ingredient. I need a way to turn an individual X into a T. Also, I'm going to use a different element type just to avoid confusion. It's not the same T as the one downstairs. Oh, keep doing that. Right.
Yeah, because this is turning an X into an A, where you're moving it from one to any function.
Right.
So
So what happens here? We've got no X's to do anything with. So what happens? I need a monoid on A, but I've got one. I'll just use the neutral element of M. Right. So here, oh, it just does a terrible thing.
the symbol is a projection of a record. You need 3 arguments in the record and then 2 arguments.
Which makes a bit of a nonsense of it being infix. Yeah. But anyway, here I need an A, and I'm going to get my A by applying F to X. And here I need another A, which I'm going to get with my recursive call. So yeah, that's all right. So yeah, there is a nice thing one could do with modules here, isn't there?
Yeah.
Anyway, the point, however, is right, so this is a general thing which says if you know what to do with one of the X's, right, so if you've got any old function in the monoids carrier type, into the monoids carrier type from the element type of the list, you get a way of turning a whole list of X's into an element of A. And we might see down the line, if we're lucky, that in fact this is the only way to make a structure-preserving operation from lists to something else, right? And it's nice that every function, right, there are no conditions on this thing here to tell you that we should prove this, in fact. But, you know, and this is the essence of it. This is the particular instance of it when we're going from lists to endo functions. But there are all sorts of things, you know, if this is like, you know, adding up a bunch of numbers or whatever it happens to be. This is your general purpose MapReduce. That's what this thing is. It's effectively map and then crush. So should we prove that this is a?
Sure.
Yeah.
Yeah.
Um,
Should I do the refactoring between the platforms?
yeah. Why don't you?
Because
and then we can do it inside the module.
It shows a bit of impact.
Oh.
Oh,
Just give me back the mic.
yeah. Oh, inside the, yeah, okay. Sure. So here it's a bit annoying because, I mean, clearly we only have one monoids in the context. So all the definitions we're gonna build are gonna be relative to this monoids. So it would be nice if we could just say, well, I'm considering this one rather than using any neutral projection out of a monoid record and then applying it to M, and then same for mapend or whatever you want to call it. So what we can do is define, so this is an anonymous records. Module, yeah, sorry. Meaning that it will automatically be opened and the definitions brought into scope. And then I can just indent this and remove the A and the monoid A here. That should hopefully still work. Yeah, the argument has been moved to the monoid, to the outside now. So I don't need to repeat it. Okay, so I'm saying in this context, I'm going to define this function. And so that's why I don't need to pass the monoid around anymore. And then the next thing to do is to say, well, I'm going to give a name. Or, well, this is nasty, but. Nope. So here I'm saying, so if you, I don't know if we've seen this already, but whenever you define a record, there's a corresponding module, parameterized module that's being generated. It's parameterized over all of the parameters of the record together with an existing record taking these parameters as arguments. So here it would be a module indexed by X and monoid X. And it contains basically all of these definitions. And then you can apply that parameterized module and you can open it so that all of the partially applied functions that are stored in it, so modulo all of the parameters, come into scope.
This open says, so I'm not opening one monoid structure in particular, I'm opening the whole concept. And that brings neutral and diamond into scope as explicitly applicable projections, but you have to apply them to a monoid structure in the nonsense. So
yeah, so it made our life easier to open monoid here because then we got short names for all of these projections. Otherwise, these projections are not in scope, and then we have the long, like dot monoid, dot diamond, dot monoid.
Well, do this job in an anonymous.
Oh yeah, okay, sure. Yeah. Yeah, whenever. Why isn't it? Yeah, but I can't select like these lines for some reason. All right. So yeah, that's nice. It's not in scope anymore. So, but that's good. Let's comment this out for now. No. Fix the module. No. So whenever you don't want to pollute the scope with whatever you're bringing into scope by opening a module, you can just shove it into an anonymous module. So these things come into scope here because we're doing the open. We can have our nice definitions. And then as we close the anonymous module, these things which were only open in that submodule go out of scope again.
The dot arc word public, which you can see not.
Oh yeah.
stuff we get from opening monoid would be part of this module and would come
They would be re-exported. Yeah.
open monoid, but only inside this module. Secretly open monoid while we work, but don't fill the big picture. So, exactly the way of not pulling the scope when it's causing trouble. And now.
And we were seeing something similar whenever we were doing proofs, and I was doing something of the shape like let open equality reasoning, right? And then we had access to the nice reasoning combinators underneath, but they were not polluting the scope. So if you're using another set of combinators to reason about like less than or something, at least they are not clashing with each other. So that's a very common trick here. So now when we move back down here, instead of naming that module, which allows me to do things like this, right? So f of x is a diamond to fold map of f of x. So that's valid. I've
dot notation for module.
Yep. So I've named, you can think of a module as being a namespace of sorts, and then you have all sorts of definitions in them. And then if you name your namespace, you get to access the definitions by saying, I mean the one that's inside A. Oh yeah, yeah. Yeah, yeah, if you were going to, if you had two monoids, then because there would be no type-directed differentiation of these things, you would need to explicitly name them. But here we have a single one. We only have, well, I mean, we have list, but we've not opened it as a monoid. The only thing we're interested in is opening A as a monoid. And because there are no clashes, we can just do it. And now we don't even need to use the explicit names anymore because
no public.
Oh yeah, once again, we don't want to pollute things. And here, what I wanted to do is this. All right, but yeah. Okay, so we've already done that actually, and we are already in the context of parametrized proofs. So here we said we have a monoid, we're going to implement fold map, and in the implementation of fold map, we're using the neutral and the diamond, but we're not using their properties. But turns out it's exactly the same once you're in an anonymous module where if you open this thing, you have access not only to the operations, but also the properties. So you might as well make use of them. And for instance, prove something like this. So if I have a set of x's and a function from x to a. Why is it so slow? Oh, my battery is about to die. Okay. And then if I have two lists, x's and y's of x values, then fold map f x's up and y's. Just want to double check that my stuff is type check-in, yeah. Is the same as, any guesses? So yeah. Oof. Right, because what's going to happen here is that we're going to turn every element in x as appendwise into a value, which will get crushed using diamonds. Whereas here we're turning the ones in x's, crush them using diamond, and then the ones in y's, crush them using diamond, and then crush the results at the very end. But because we have a monoid, the order in which we perform the operations doesn't matter. The only thing that matters is the left to right order of the values that are being crushed. Okay, so I have f, x's, y's. And here we're playing the game of why is it stuck? So here, I mean, it's stuck on both x's and y's. Here it's stuck on this compound expression, which is built using append, meaning that it's stuck on x's. So we have 2 votes for x's, 1 for y's. So let's start with x's, and we'll see whether we need to look at y's eventually or not. Okay. So in the base case, here empty list append y's is just y's, which is what we get here. But here we have the diamond on the outside, meaning that x's is isolated. It is the empty list, so fold map of f of x's reduces to the neutral element. Luckily for us, we know that using the neutral element on the left doesn't change anything. So we can just appeal to the results here. And then in this other case, it's not, okay. We'll need 2 steps. So here we have f of x on both sides, but here it's nested to the left of this thing. So we probably want to use associativity to move the parens to the right, and then we'll have the same fx on the outside, meaning we can use congruence to get rid of it. And then, well, let's do that actually. So I'll open equality reasoning n. So I have begin, which I always type being. Also, I like to put it on the previous line. Oop. Mm. All right, I hope this will be enough. A bit of solving. Okay, so this one, we can do a bit of computing. Yes, thank you. This one, I said I wanted to reassociate to get fx on the outside. So that should be, it's either diamond a sock or diamond a sock, or the symmetric of it. So it's going to take fold map fx's, fold map fy's. Okay. It's the symmetric. I'm going to do this thing because I'm annoying. This is the same combination, but going the other way, so that I don't have to say sim explicitly. And here, oh, here we have a bit of computation too. Oh no, my brackets are the wrong way around. My copy pasting stuff. Up, up, up. Yes. So let's do a bit of computation. All right. I'm really happy now because I got my fx diamond on the outside, so I'm gonna get rid of that before even looking at anything else. And now if I look at the goal, this is exactly the result of the induction hypothesis. So we can just call this thing fold my plus plus. All right. We got there just in time.
Cool. I'm very careful these days. I do talk about these ideas with first years, but I tend to avoid long Greek words. So you've got a situation where you've got multiple instances of the same structure, which equips some underlying type with a bunch of operations and a bunch of laws. And if you've got a function which maps the carrier type from one structure to the carrier type for another, so here our carrier type is list X for where we're starting, and here our carrier type is A. Yeah, if you've got a function, then if you can prove this property, we're turning lists into A's. If you can prove that it takes the neutral element, if it takes all the operations from one of the structures and turns it into the source structure and turns it into the same operations but for the target structure. So neutral element goes to neutral element. A combining operation, in this case, append, turns into the diamond. That's not just any old function. That function is a homomorphism for that structure. Homomorphism is Greek for same shape, right? So it's a way of saying we actually turn the whole picture of these computations into the corresponding picture in the other structure. And these things are why we even bother to notice structure in the first place.
Perfect.